Hello everybody guys, welcome to Unit 5 review. Guys, this is my first time trying to record a lesson for you, so if you see me pause or lose audio for a second or something, I'll try to fix it later. If not, I'll try to fix it for future videos. So bear with me on this one. This is my first attempt at this. So what I'm going to do is take you guys through Unit 5 review. This is a study tool. We'll be going over this in class, so you guys will have already seen some of these problems probably done. This gives you a chance to kind of look back at these problems and have me walk through them at your own pace. Remember guys, you can always pause the video at any time. You can fast forward, rewind, whatever you need to do. That's up to you. So let's get moving with this. So if we look at example 1 here, it says solve the following system of equations graphically. So the first thing we should notice, guys, is that this system of equations is not linear. Okay, it's a mixture. So what we have here is we have a quadratic, and remember guys, we can recognize that's a quadratic by the x squared term, and then we have a linear. So this is a mixture. Alright, now if you guys remember, we did these back in 5.2. Alright, 5.2. which was solving other systems of equations. Now, guys, we're going to solve this graphically just like we would solve any linear system. We're going to make sure that both equations are equal to y. We're going to graph them together on the same plane, and we're going to look for the points of intersection. So, if we notice, the quadratic is already set equal to y. So we're going to focus our attention right now on this linear equation. So what we're going to do is we're going to take this linear equation, guys, and we are going to go ahead and solve for y. So just a simple reverse PEMDAS here. Going to do the old switcheroo there, 4x plus 2, and then everyone gets that division by 2. We're going to get y equals 2x plus 1. Now, as per usual, guys, with these systems, I'm going to go ahead and call the quadratic A, and I'm going to call the linear equation B. Now, just for simplicity, guys, I'm going to start with the linear equation, graphing the line, because this is a little bit simpler than graphing the quadratic. So we're going to start with this line, which has a y-intercept of 1, so I'm going to go over to my graph. Start with that y-intercept of 1. It has a slope of 2. That's up 2 over 1. So I'm going to continue that pattern until I get as many points as possible on the graph. And then we're going to use a ruler. Go ahead and draw a nice straight line through here. Okay, I'm a little off there. Let's redo that. Bear with me here, guys. I'm one-handed here because I'm holding the mic, so we're going to call that good for right now. I know I missed a couple points down here at the bottom. So we're going to call this B. This is our B equation, our linear. Now, to graph this quadratic, there's a couple of ways, guys. We could make our own table, but the easiest way, as most of us know, to graph this quadratic, y equals x squared minus 5x plus 7, is to go ahead and we're going to go, once I figure this out, give me 1 second, guys. Okay, we're frozen here. Hold on. Bear with me, guys. 1 second. Here we go. So let me get out of teaching mode here. Okay, here we go. So what I'm going to do, guys, is I'm going to go ahead and I'm going to pull up the calculator. Now, I know a lot of you don't have the calculator at home. That's okay. Just pay attention to the keystrokes that I'm doing. I'll walk you guys through this. So remember, in order to graph, we want to go to y equals, I'm going to clear out anything I have there, and I'm going to type in x squared, and that was minus 5x plus 7, minus 5x plus 7. Now we don't want the graph, guys, we want the table, which is second graph. And if we look at my table right now, we notice that it's going by halves. This is because I was doing something earlier. Now, we don't want it to go by halves, guys. We want it to go by ones right now. So if you recall, I did show you how to change the table. It's second window. It brings up this little menu for us. Now we typically want to start our table at 0, which it is, but this table change right here, this little triangle, that means change, guys, if you remember that from class. This is going to tell us or control our table, what our units go by, and we want to go by ones. So if I go back to the table now, second graph, now as you guys can see, my table is going by ones. Now, remember, guys, with these quadratics, we get these repeating y values. You guys see it goes 21, 13, 7, 3, 1, 1, 3, 7, 13, 21. You get that repeating pattern. Remember, these quadratics are symmetrical. Okay, they're symmetrical. So what I'm going to do, guys, is I'm going to use these points, and I'm going to go over to my graph, and I'm going to go ahead and plot these points. Now, I'm not going to be able to fit the 21s on there, and probably not even the 13s, but I can fit 7, 3, 1, 1, 3, 7. So I'm going to start at 0, 7. So there's my first point at 0, 7. My second point is 1, 3. Two, 1. 3, 1. And then, guys, we get that symmetrical pattern here. Now, we're actually missing, you guys might recall, it's called the vertex. We're missing the vertex. There's actually a point somewhere in here that we don't know what it is right now, and that's for later units. But for right now, what we're going to do is I'm going to draw my U shape, my parabola shape through, and I'm just going to give a little turn down here. I'm going to give a little turn. Now, there's our graph A. Now, you guys might notice right off the bat, what we've got here is we can clearly see that there is one intersection point right here. Remember, we circled that up, and I'm going to go ahead and write that over here. That is the point 1, 3, okay? So that is our first solution. Now, here's a problem, guys. There's actually another solution on my graph, but as we can see up here, the graph doesn't go high enough for us to see that second intersection point. So we're actually going to go to the calculator and have the calculator help us find that second intersection point. So what I'm going to do is I'm going to go to Y2, and I'm going to change this back to a line because if you guys remember, we were working with inequalities in the calculator. So I'm going to change that back to a line, and what I'm going to do is I'm going to graph the linear equation y equals 2x plus 1. I'm going to go to the table, guys. I'm going to go to the table. Now, if you guys look at x equals 1, both of the y values are 3, and we already have that point, 1, 3. We already have that. We're looking for the next intersection point that we can't see on our graphs. And if you guys look closely, here at x equals 6, we can see that the two y values are both 13. So our second solution, even though we can't see it on our graph, is the point 6, 13. Now, guys, be prepared for these type of systems, these nonlinear systems where you get a linear and then a different type of function. not just for quadratics, but if you guys do recall, we did do some work with absolute values and linear equations. So I'm just going to show you guys really quick, just in case you forgot, where the absolute value sign is. It's under math, over a number, and number 1 is absolute value. Now remember, guys, on the older calculators that we have right now, you won't get the double bars. You'll get the ABS on your calculator, which stands for absolute value. All right, so that wraps up number 1 for us, guys. Graphing nonlinear systems. So moving on to number 2. Number 2 says solve the following systems of equations algebraically. So guys, we have here is a basic system of equations, no word problems, just 2 linear equations that we want to find the solution to. Now, if you guys notice, these are what we call stacked and aligned. And when they are stacked and aligned, we want to use elimination. And recall that when we're using elimination, we want to get opposite coefficients in front of one set of variables. Now, guys, oftentimes one of the variables is easier to eliminate than the other. And in this case, if we look at the y's, we've got a 3 and a 1 in front of the y's, and then in front of the x's, we have a 5 and a 3. It is much easier to get opposite coefficients for the y's in this case, because what I can do is if I multiply the second equation by -3, that'll give me a -3 in front of that y. Now, don't forget, guys, when you do multiply, we are going to go ahead and distribute through. So our new equation is going to be -3y minus 9x equals -21. And then recall what we're going to do, guys, is we're going to bring down that original equation that we did not manipulate, and we're going to restack them. And then we are going to add this system together. And we get that elimination effect. The y's cancel. -9x plus 5x is -4x. -21 plus 9 is -12. So now, guys, we just have a one-step equation to solve. Divide by -4, x equals 3. Now, this is only half our solution, guys, because don't forget, we need the y value as well. So what we're going to do is we're going to take that x equals 3, and I'm going to plug it back into one of the original equations. So I'm going to go with y plus 3x equals 7. I'm going to plug in for x. And I am now going to solve for y. So I'm going to get y plus 9 equals 7. Subtract 9. Y equals -2. So therefore, guys, my solution, remember we always express it as a point, is 3, -2. Now, don't forget, guys, you always can check your answer. Remember, in this case, we would check in the equation that we didn't plug into here. So if we were going to check this, we would plug this into this guy here and see if it works. So remember, when you check, plug into the one that you did not use here to get your second variable. All right. So let's move on to number 3. Again, guys, we have another system here. Solve the following systems of equations algebraically. Now, guys, remember, when they tell you to solve something algebraically, they're really usually giving you a choice here. Remember, it's a choice between elimination and substitution. So in this case, if we look here, we notice that these two equations, these two linear equations, they're not lined up. All right? We can clearly see that the equal signs aren't lined up. And although it appears that the y's, the x's, and our coefficients are lined up, the equal signs are clearly not in line here. So these are actually not ready for elimination. Instead, if we look at this first linear equation, we notice that the y is alone. Guys, when the variable's alone, this is a dead giveaway that we are going to use substitution. So recall, since y is equal to 3x minus 1, that tells me that wherever else I see a y, I can now plug in 3x minus 1 for that y. Well, guys, in our second equation, there's a y right there. So what we're going to do is we're going to take this 3x minus 1, and we are going to substitute it in for y. Remember, guys, this is the substitution method. Now, why are we doing that, guys? Because now what we have is we have one equation with simply x's in it. And now what we're going to do is we're going to go ahead and solve, and we're going to start by distributing. We're going to distribute. We're going to get 6x minus 2 minus 4x equals 6. We're going to get a couple of like terms there. We're going to combine those. 6x minus 4x is 2x. Now we've got reverse PEMDAS. So we're going to add 2 over. We get 2x equals 8. Divided by 2. We get x equals 4. Again, guys, remember that's only half our answer. We're going to take that 4. We're going to plug it back into one of the originals. Typically, we want to go ahead and plug that back into the one that was solved for y. Just going to be easier for us. So we're going to take y equals 3x minus 1. We're going to go ahead and plug that solution in for x. Notice, guys, I'm always using parentheses when I'm making a substitution. And we're going to get y equals 11. So our solution point, guys, the point of intersection, remember this is the point of intersection between these two linear equations, is 4, 11. And once again, guys, you're more than welcome to check that. Remember, we would want to check that in the one that we did not plug back into to get our second answer. Moving on. So, number 4, switching gears a little bit here, we've got solve the following system of inequalities. Be sure to label your solution area with S. So, these are more recent for us, guys. If we remember, we've been working with these the past few days. We don't have a word problem attached to these, so we just have a couple of inequalities here. And recall that the only way to solve a system of inequalities is by graphing. And since we're going to need to graph these, again, just like with equations, the y needs to be alone. So the first thing we're going to do is we're going to take each of our inequalities. I'm going to start with y minus 3x is less than 1, and we're going to go ahead and solve this for y. So I'm going to go ahead and add my 3x over to the other side, and we're going to get y is less than, we're going to switch those terms, 3x plus 1. And let's call this inequality A, guys. So now I'm going to take my second inequality. 2y is greater than or equal to negative 3x. Again, we're going to get that y alone by dividing by 2 on both sides. And I'm going to get y is greater than or equal to negative 3/2 x. And we're going to call this guy B. Now remember, guys, when you are graphing inequalities, you must keep in mind 2 things. Is the line solid or dotted? And do I have to shade above or below? So starting with inequality A, we notice that the slope is 3 and the y-intercept is 1. So I'm going to start at the point 0, 1. I'm going to use my slope of 3. That's up 3 to the right 1 to get as many points as I can. Remember, in reverse, that's down 3 to the left 1. Now, this is where we got to be careful, guys, because I know we're used to graphing equations, and we just go ahead and put our ruler down and draw a line through. But recall that since there is no equal to under this inequality, this is going to be a dotted line signifying that the points on this line are not part of the solution to the inequality. And now that we have that, we focus on the shading. Recall, guys, this is y is less than 3x plus 1. Where are the less than y values? Below the line. So we're going to go ahead and shade below the line. And we're going to label that A. And then we're going to move on to B, which is y is greater than or equal to negative 3 halves x. Remember, guys, there is a y-intercept here. It's technically plus 0. So I'm going to go ahead and throw a point there at the origin, 0, 0. And I'm going to use my slope of negative 3 halves, down 3 to the right 2, to go ahead and get my points. Or that's up 3 to the left 2 if we're working backwards. Now, guys, pay attention here. This one is equal to, greater than or equal to, so we can go ahead and use a solid line. Don't forget your arrows. And since this one is greater than or equal to y, the greater than y values are found above that line. We're going to label that B. Now, our last step here, guys, remember, we're looking for the double shaded region, which we can clearly see is on the right portion of this graph. And we're going to go ahead and throw a capital S over there, S for solution set. And you can go ahead and circle that if you want to. That's letting the reader know that you understand that the solutions to the system of inequalities are found in that region. Now, they hit us with a question here at the end. They say, is the intersection point of the two inequalities included in the solution set? Give an explanation for your response. So, guys, here's that intersection point right here. There it is. Now, it doesn't matter that we don't know that intersection point because they don't ask for it, but we should recall that an intersection point that includes a dotted line is not in the solution set because dotted lines indicate that the points on that line are not part of the original inequality. So in this case, we would answer no, because graph A has a dotted line. And guys, there's a lot of different ways that we could word this. I would say that this is the most simplistic way, easy way to remember. Remember, if we can keep our explanations short and to the point, it leaves less room for us to make errors and kind of ramble on. So if we can keep it short like this, that's the best way to go. Okay, let's move on to number 5. So we got some words here. It looks like a word problem. So a gardener is planting 2 types of trees. Type A is 3 feet tall and grows at a rate of 15 inches per year. Type B is 4 feet tall and grows at a rate of 10 inches per year. Algebraically determine exactly how many years it will take for these trees to be the same height. Now, the first thing that jumps out, and hopefully jumps out to all of us, guys, is that really that key word that I've made a point in class, same. And we should remember that when we see same, that means equals. So we might conclude that we're going to go ahead and set up some type of equations. And we might be taking these equations and setting them equal. Now, if we read this last sentence again, it says, algebraically determine exactly how many years it will take for these trees to be the same height. Now, if you guys recall, I told you that when we get these word problems for these systems, always look at that last sentence and you'll usually find your let statement or statements. But in this case, we're actually only going to have one let statement. We're going to let x equal the number of years. Now, you're more than welcome to use a different variable. I'm just going to use x to keep it simple. Now, guys, this is one of those examples, and I'm sure you guys can clearly see this. It's got those 2 separate scenarios. You know, we've got type A tree and we've got type B tree, clearly indicating that each tree is likely to have its own equation. So we're going to go ahead and we're going to write an equation for type A, and we're going to write an equation for type B. Now you guys might recall that in class we did, A equals and B equals. You're more than welcome just to do Y equals for both, but we want to always be prepared for the regions, and the regions may do something like this. So type A is 3 feet tall and grows at a rate of 15 inches per year. Type B is 4 feet tall and grows at a rate of 10 inches per year. Now, this might not be obvious to most of us, but some of you might have noticed that within each of those sentences, there were 2 different units of measurement. They say that the tree is 3 feet tall, but then they go on to tell us that it grows at a rate of 15 inches per year. Guys, the regions will do this. They will try and confuse us by giving us different units. Now, we can't have an equation with 2 different units in it. So we either have to use all feet or all inches. In this case, guys, it's easier to convert our feet to inches. So instead of using 3 feet, I'm going to go ahead and use 36 inches. Remember, guys, there are 12 inches in a foot. So if type A tree is 3 feet tall and grows at a rate of 15 inches per year, that 15 inches is going to be our slope, and our initial height, or our y-intercept, is going to be 36. Now, same thing for type B, guys. They tell us that it's 4 feet tall. So a really quick conversion, 4 feet is 48 inches. Now, type B tree only grows at 10 inches per year. So B is going to be 10x plus our initial height of 48 inches. Now, if you guys recall from class, whenever we have these 2 different equations like this and they want us to find when they're the same, we essentially are going to use substitution, or what some of you might say, set the 2 equations equal. So we're going to take 15x plus 36 and set it equal to 10x plus 48. Guys, what we're doing here is we're really just taking the type A tree height and we're setting it equal to the type B tree height to figure out the number of years it will take for these 2 trees to reach the same height. And guys, now we're just going to go ahead and solve this. All right. So most of us are going to go ahead and probably get our x's to the same side first. So I'm going to subtract 10x over to the left side so I don't have to deal with any negative x values. So I'm going to get 5x plus 36 equals 48. I'm going to go ahead and subtract 36 from both sides, a little reverse PEMDAS. We're going to get 5x equals 12. We're going to go ahead and divide by 5 on both sides. And we're going to get x equals 2.4. Now, typically, guys, with systems, we usually have to plug this back in to get another part of the answer. But they simply asked here for the number of years it will take for the trees to be the same height. They didn't ask for the height that the trees will be. They just wanted to know how many years it will take. So, guys, we're simply going to say that it will take 2.4 years for the trees to be the same height. And we are done. So remember, guys, we had those 3 different scenario types for systems of equations. This is that type where we have 2 clear scenarios going on. Type A, Type B, Tank 1, Tank 2, Plan 1, Plan 2. Each one gets its own equation. And remember with these that there's only one let statement. Okay, let's move on. Okay, so number 6, a high school drama club is putting on their annual theater production. There is a maximum of 800 tickets for the show. I'm actually going to go ahead right now. That sounds like something important. So there's a maximum of 800 tickets for the show. the cost of the tickets are $6 before the day of the show and $9 on the day of the show. Seems important. To meet the expenses of the show, the club must sell at least $5,000 worth of tickets. I'm going to go ahead and box that in as well. Actually, I think I'll box this in too. And you guys might, some of you might already know why I'm boxing those in. So part A says, write a system of inequalities that represent this situation. Now, before a lot of us even read A, we might have known that we were going to set up inequalities because of some key words in there like a maximum of 800 tickets and at least $5,000. Those are some key words that tell us that we have, remember what they're called? Constraints. Constraints, guys. Very important word. The Regents will use it. Okay? Constraints. Remember, those are the things that are restricting us in the problem. So for part A, we're going to go ahead and write our system of inequalities. Now, I'm going to start with the two constraints, guys. So the first constraint was 800. And that had to do with the tickets. That's as many as they can sell. So we're talking that the number of tickets they sell must be less than or equal to 800. So this has to do with tickets. The $5,000, that's the amount of money they must make. So they must sell at least $5,000 worth of tickets. So at least, guys, is greater than or equal to 5,000. And remember, this is money. This is money. Now, a little different here because we were used to these with a problem giving us the let statements. Now, they don't actually give us let statements here. I don't see it anywhere in the problem. So we are going to need to come up with let statements on our own. So down here at the bottom, we're going to have a couple of let statements. Let X, let Y. Now, guys, we clearly see that what the two different things that they're talking about here. We're talking about two types of tickets. We've got the number of tickets sold the day before the show, and we've got the number of tickets sold the day of the show. Now, guys, don't forget those let statements. But do remember, if they give them to us in the problem, we do not need to write them down. So I'm going to come over here. I'm going to finish these inequalities up. So for my tickets inequality, less than or equal to 800, remember, guys, 800 represents tickets. Well, my let statements also represent tickets, X and Y. So here I know that the number of tickets sold the day before and the day of have to be less than or equal to 800. Now, for my money inequality, remember, guys, money, money, money. If there's money on the right, there's going to be money on the left. That's where this $6 and $9 comes in. It is $6 the day before and $9 the day of. Now, there's our system of inequalities. It is all set. And that answers part A. They don't want us to solve it. They just want us to write a system of inequalities that represents the situation. So now we're going to go ahead and direct our attention to part B. Part B says the club sells 440 tickets before the day of the show. Is it possible to sell enough additional tickets on the day of the show to at least meet the expenses of the show? Okay, so they tell us that the club sells 440 tickets the day before. So that is telling us that X is equal to 440. Well, guys, if they sold 440 tickets the day before, and there's a maximum of 800 tickets that are potentially can be sold, to get our Y value, we're just going to go ahead and take those 800 and subtract from it the 440 that were sold the day before to give us 360. So this is our y value. So we're assuming, guys, if they have a full house, that they're going to sell 360 tickets the day of. Now, we're not so much concerned about that. We're concerned about if they're going to make enough money. So let's drag this up a little bit here. So you guys might recall we've done a problem like this. We're going to go ahead, we're going to take our 440 for x and our 360 for y, and we're going to plug that into our money inequality, which is 6x plus 9y is greater than or equal to 5,000. And we're going to go ahead and make those substitutions. So 6 times 440 plus 9 times 360 is greater than or equal to 5,000. We got a little bit of math to do here, so probably going to pull up our calculator for this one. So 6 times 440, 2640. 9 times 360, 3240. And if we go ahead and add those two numbers up, we are going to get $5,880, which luckily for the club is greater than or equal to 5,000. So to answer the question, is it possible to sell enough additional tickets on the day of the show to meet the expenses? Yes. The club could make $5,880. Now remember, guys, the real question there was if the club was going to make enough, and that's because the more tickets they sell the day before the show, the less money they're going to make, because the day before tickets were less than the day of tickets. So there could be some concern there if they sold a lot the day before, that they wouldn't have the potential to meet their expense goal, which was 5,000. But in this case, the 360 on the day of would be enough for them, and there's actually plenty of room there even if they didn't get the full 360 on the day of the show. Okay, let's move on. Number 7, Wolfrich lived in Portugal and Brazil for a total period of 14 months in order to learn Portuguese. He learned an average of 130 new words per month when he lived in Portugal, and an average of 150 new words per month when he lived in Brazil. In total, he learned 1,920 new words. How long did Wolfrich live in Portugal, and how long did he live in Brazil? So once again, guys, if we read that last sentence, there's two questions being asked here. How long did Wolfrich live in Portugal, and how long did he live in Brazil? And I'm sure some of you guessed it, those are our let statements. So we're going to go ahead and let x equal the months in Portugal, and we're going to let y equal the months in Brazil. Now remember, guys, there's got to be enough information in the problem for us to set up a system of equations here. So if we go back to the beginning, they tell us that Wolfrich lived in both of these places for a total period of 14 months. So that's should be a familiar word to us, total, right? So guys, we like totals because usually it's pretty easy, because we know that if we have a total amount of something, in this case total months, that's the months in Portugal and the months in Brazil. So that's just simply x plus y. Now, they also give us another total down here. They say that he learned 1,920 new words. Now, if we've got, remember guys, if we've got words on the right side, there must be something to do with words on the left side, and that's where these averages of 130 new words per month in in Portugal, and 150 new words per month in Brazil come in hand for us. So he learned 130 new words per month when he lived in Portugal, so that's going to be 130x, plus the 150 per month he learned in Brazil, which is going to give us 150y. So, guys, remember, this is probably the hardest part for most of us, is setting up these equations. But now that we have them, we simply need to ask ourselves, what is the best algebraic method for us to solve this? And if we recognize these are stacked and aligned, the x's, the y's, the equal sign, the coefficients are all lined up, we're going to go ahead and use the elimination method. So this is actually nice because the x's and the y's only have 1's in front of them. So we either need a negative 130 in front of the x or a negative 150 in front of the y. And I'm just going to go ahead and I'm going to eliminate the x's, so I'm going to multiply through by a negative 130. And don't forget, guys, we're distributing all the way through this. Okay, 14 times negative 130 is negative 1,820. So remember, guys, we're going to go ahead and add these, and we should get that elimination effect, which we do with the x's. 150y plus a negative 130y gives us a 20y. 1920 minus 1820, that's going to give us 100. We've got a one-step equation to solve. And we're going to get y equals 5. Now, remember, guys, it's only half our answer here. We have two let statements, so we need two answers. So we're going to take our y equals 5. We're going to plug that back into one of the original equations. We're going to go with x plus y here. X plus y equals, I believe that was 14. Yes. We're going to plug that 5 in for y, and we're just going to go ahead and solve for x. Now, some of us might not need to do this. We might just be able to do that subtraction in our head. Oop. And we're going to get that x equals 9. So now, guys, all we have left is a sentence. Wolfrich lived in Portugal for, Portugal was our x, so that's 9 months. And in Brazil for 5 months. Remember, guys, once we have our sentence, we're all set. We're all set here. So in terms of the scenarios that we talked about, guys, those 3 scenarios, this is one where we get a total, just a plain old total, and then another total, and we're used to getting a total of money, but in this case we got a total words that he learned. But I know that we're used to money, but don't fall into that, oh, it's always going to be money. It's not necessarily always going to be money. In this case, like I said, this equation right here, this was a words. But as you guys can see, they follow the same format. You're going to get that elimination set up. The work's going to be the same for the most part. Okay, let's move on. So number 8, Bavik bought 3 liters of milk and 5 loaves of bread for a total of $11. A month later, he bought 4 liters of milk and 4 loaves of bread at the same prices for a total of $10. How much does a liter of milk cost, and how much does a loaf of bread cost? So, guys, I probably sound like a broken record here, but that last sentence is so important. How much does a liter of milk cost, and how much does a loaf of bread cost? Those are our let statements. So let's let x equal the cost of the milk, and let's let y equal the cost of the bread. Now, some of you, I'm sure, right off the bat could tell what scenario this was, because you guys always hear me say it in class, kind of weird. You know, someone goes somewhere and buys some of these and some of those for a total, and they usually go back and buy some of these and some of those again for a different total. So this is that scenario. So two clear situations going on here. His first trip and then his second trip that he makes. So his first trip, he bought 3 liters of milk and 5 loaves of bread for $11. So we're going to get 3x plus 5y equals 11. And then his second trip was 4 liters of milk, 4x, and 4 loaves of bread for $10. Now again, guys, we are stacked and aligned here. We are all stacked and aligned. So we're going to go ahead with the elimination method. Now, whether we choose x's or y's here, if you guys notice, we've got a 4 and a 3 in front of the x, and a 5 and a 4 in front of the y's. No matter which one we choose, guys, we're going to have to manipulate both equations to get to a common multiple. So if we choose 4 and 3, we're likely going to go with 12. And if we choose 5 and 4, we're likely going to go with 20. I'm going to go ahead and go with 4 and 3 just because they're a little bit smaller to work with. Completely up to you guys. So remember, one of them has to be positive, one of them has to be negative. So I'm going to multiply this first equation by 4 and the second equation by negative 3. And remember, we're distributing through. And we're going to get a brand new system. So we're going to get 12x plus 20y equals 44, and then negative 12x minus 12y equals negative 30. Now guys, do recall that although this system looks different, it is going to have the exact same solution as the original system because all we did was use the multiplication property of equality, which says that if we multiply an equation through by the same number, that we're not changing the equation. Okay? So this system is still going to have the same exact solution. So we're going to go ahead, we're going to proceed, we're going to add these together, we're going to get that elimination effect on the x's. 20y plus a negative 12y is 8y. 44 plus a negative 30 is 14. And if we divide by 8 on both sides, looks like we're going to get a decimal here. 14 divided by 8, we get $1.75. Now remember guys, that's just the cost of our loaf of bread. We do have a little bit of work to do left to find the cost of the milk. We're going to take one of those original equations. Remember guys, we always go back to the original. We're going to go ahead and plug in that $1.75 for y. So we're going to get $8.75. And now we've got a two-step equation to solve. So we're going to get 3x equals 225 divided by 3. 225 divided by 3, let's see what we got here. 75 cents. Now that we have our x and y, guys, all we have left to do is write our sentence. So the milk costs 75 cents and the bread costs $1.75. And we are done. Let's move on. Okay, so number 9 here, looks like we got another word problem. Loretta and her family are going on vacation. Their destination is 610 miles from their home. Loretta is going to share some of the driving with her dad. Her average speed while driving is 55 miles per hour, and her dad's average speed is 65 miles per hour. The plan is for Loretta to drive for the first 4 hours of the trip and her dad to drive for the remainder of the trip. Determine the number of hours it will take her family to reach their destination. Now, I will point out here that in that last sentence, they don't really make it clear what our let statement should be. But I'm hoping at this point, guys, that we can kind of see the two unknown things here. They're talking about Loretta driving and her dad driving. So what we're going to do is we're going to go ahead and let X equal the hours Loretta drives. And we're going to let Y equal the hours that her dad drives. Now, they do give us quite a bit of information here. So let's start with the fact that their destination is 610 miles from their home. Now, there's some other things in here that talk about miles. In this case, miles per hour. They say that Loretta's average speed is 55 miles per hour, and her dad's average speed is 65 miles per hour. So remember, guys, you're going to keep units consistent through each equation. So in this case of this first equation, we're going to have the 55, which is the speed of Loretta, times the number of hours Loretta drives, plus 65, which is the dad's speed, times the number of hours he drives, and we want that to be equal to 610. Now, this is one of those ones that's a little bit more difficult because the next equation is given in terms of a relationship between the number of hours that Loretta drives and the number of hours that her dad drives. And it says that the plan is for Loretta to drive for the first 4 hours of the trip and her dad to drive for the remainder of the trip. So, somehow we've got to set up a relationship between X and Y in which Loretta drives the first 4 hours and her dad drives the rest. So basically what we're saying is, guys, is that after the first 4 hours, her dad is going to drive the rest, even though we don't know what the rest is yet. So let's say that Loretta's dad sorry about that, guys. So let's get back to the problem here. The plan is for Loretta to drive for the first 4 hours of the trip and her dad to drive for the remainder of the trip. So what they're kind of doing here, guys, and we actually don't even need to set up a relationship between X and Y. They're telling us that Loretta is going to drive for 4 hours. So it's as simple as X equals 4. Now you might say, well then how are we supposed to know how long her dad drives? Well, guys, we're going to figure that out because now that we know that X equals 4, that Loretta is driving for 4 hours, we can go ahead and substitute that in to our original equation, 55x plus 65y equals 610. So let's go ahead and do that. So 55 times 4 is 220. If we subtract the 220 over, we're going to get 65y equals 390. So we're going to divide by 65 on both sides. So 390 divided by 65 is 6. Now, we do have to be careful here, guys, because the question asked was determine the number of hours it will take her family to reach their destination. So they don't even care how many hours Loretta drives and how many hours her dad drives. They want to know the total hours. So all we're going to do is we're going to take the 4 and the 6 and we're going to add them for 10 hours. Now there is a second part to this question. It says, after Loretta has been driving for 2 hours, she gets tired and asks her dad to take over. Determine to the nearest tenth of an hour how much time the family will save by having Loretta's dad drive for the remainder of the trip. So guys, we should kind of know that the less time Loretta spends driving, the less time it's going to take for her family to get to her destination because her dad drives at a faster rate. So now what we're saying is we still have the same original equation here, 55x plus 65y equals 610, except our second equation is now x equals 2 because she's only going to drive for 2 hours. So what we're going to do, again, we want to figure out how long her dad's going to drive for. So we're going to plug this in. So we're going to get 110 plus 65y equals 610. Let's go ahead and solve for y. $65y equals 500. That's a 5 there. Divide by 65. Now, guys, we almost know we're going to not get a nice answer here because they told us that we're going to have to round. So 500 divided by 65. Is that not a nice number? Now, if we go back and look here, it says to the nearest tenth of an hour. So what I'm going to do, I'm going to round this off to the nearest tenth. So if we look, we have 7.69. So we're going to round that up to 7.7. Now, that's not our answer because the question is, we want to know how much time the family will save. So if before they were going to take 10 hours and now they're only going to take 7.7 hours, we're looking at 2.3 hours saved. Guys, remember, especially on the Regents, always go back and read the question again to make sure you've answered the question they've posed. I know it's easy to get down and get an answer, and you're excited because you know you got y equals 7.7, and you're okay with that, but remember that's not always the final answer. Make sure you go back and reread the problem. All right, so last question here. Looks like a doozy. Edith babysits for X hours a week after school at a job that pays $4 an hour. She has accepted a job that pays $8 an hour as a library assistant working Y hours a week. She will work both jobs. She is able to work no more than 15 hours a week. Oh, that sounds important. I'm going to go ahead and box that in. Sounds like a constraint. Due to school commitments, Edith wants to earn at least $80 a week. Sounds like another constraint there. So he's going to work a combination of both jobs. So write a system of inequalities that can be used to represent the situation. Graph these inequalities on the set of axes below. In this case, off to the side. So, guys, we see our words in there that tell us that we're dealing with inequalities. No more than, at least. Now, the other nice thing is our let statements are provided to us. It says that babysitting hours are represented by X and library assistant hours are represented by Y. So I'm going to focus on our constraints. I'm going to start with the 15. No more than 15, guys. That is less than or equal to 15. Now remember, this is hours, so we need hours on the left. What are the hours? Well, X represents the hours for babysitting, and Y represents the hours for library assistant. Now, looking at the $80 per week, he wants to make at least 80. That is greater than or equal to 80. So we got money, so we need money on the left side, and they do provide us with those per hour rates. Edith is going to make $4 per hour babysitting and $8 per hour as a library assistant. Now guys, it is very, very tempting to look at this and say, oh, we're going to use the elimination method to solve this. But then we're going to remember that we can't, because inequality systems cannot be solved algebraically. They must be solved graphically. And in order to solve them graphically, they must be solved for y first. So we're going to take both inequalities and we're going to go ahead and we're going to solve those for y. So for my first one, I'm going to get y is less than or equal to negative x plus 15. I'm going to take my second inequality. Let's go ahead and subtract that 4x over. 8y is greater than or equal to, remember guys, we're going to flip those terms, negative 4x plus 80 divided by 8. We're going to get y is greater than or equal to negative 1/2 x plus 10. And let's call this one b and this one a. Remember guys, we do that just to simplify our labeling. Now guys, typically the first thing we would focus on is getting our scaling done. But if we look, actually, this is already scaled for us, which is great because now we don't have to worry about looking at the y-intercepts and determining what we should make our scale on the xy axis. It looks like they just want by ones. So perfect, that's done for us. However, what we do need to do is label our axes. And since x is the hours for babysitting, we're going to label our x-axis as hours babysitting. And as on the y-axis, we're going to do hours as a library assistant. And guys, now we're ready to graph. So we're going to start with A. A has a y-intercept of 15 and a slope of negative 1. That's down 1 to the right 1. Remember guys, since the x and y axes are the same scaling, every box is a 1-to-1 ratio. So the slope is just perfect for us. It's perfect for us. Now this is less than or equal to, so we're going to go ahead and use a solid line. And it's less than, so we're going to shade below. And we're going to label this A. I'm going to hop colors here. We're going to look at B. B's y-intercept is 10. And B's slope is negative 1/2. That's down 1 to the right 2. Guys, this is also going to be a solid line because of the equal to, but this one is y is greater than or equal to, so this one we'll be shading above on. And I'm sure as we're all familiar with now, we're looking for that double shaded region, and we're going to go ahead and throw our capital S for solution set right in that double shaded region. Now as for the regions, they do like to ask you guys another question, which we do have one here. It says determine and state one combination of hours that will allow Edith to earn at least $80 per week while working no more than 15 hours. So guys, really we're just picking a point that meets both constraints, or we're picking a point that falls in the solution set. So all we have to do is go up to our graph and pick a point that falls in that double shaded region. And I'm sure you guys remember me saying this. Please pick a point that is not close to the boundaries. So I'm thinking maybe this guy right here, kind of in the middle, which looks like it's the point 2, 11, which is 2 hours babysitting. And 11 hours at the library. Alright guys, well I hope this was helpful for you. I'm looking forward to doing this quite a bit. You guys can give me some feedback on this. Hopefully a lot of you are using it. I'm sure a lot of you are using it differently. You don't have to watch the whole video. If you've got this far and you've watched the whole thing, that's great. Like I said, I hope it's helped you guys. I will see you on Tuesday, test on Tuesday. Have a great weekend.